Okay, let me see if I can go through this pretty quickly. On part 2 of your chapter 4 exam, to be given on Monday, you're mostly focusing on applications of the derivatives. And so if you look at the first example, this is a typical type of related rates problem. So the spherical balloon is inflating with helium at a rate of 128 pi cubic feet per minute. That is volume changing over time. So that is a dV/dt. And so I make note of that. And then the question says, how fast is the balloon's radius increasing at the instant the radius is 4 feet? How fast is the surface area increasing? So actually 2 questions that need to be answered in this problem. So what we need to do is think about our equation, our formula that we're going to use. And that turns out to be this one. So we have the volume formula. We start there. Once we have our volume, we know that we have a dV/dt information that we're given. So I'm going to take the derivative. I could do a list of information I have, knowns and unknowns, what I need to know. But I'm going to jump right to the dV/dt, the derivative of the volume with respect to time. So that gives me this second line here. And then after that, I know I want to find, the first question is asking how fast is the radius changing when the radius is 4 feet. So you can see that plugging in the dV/dt, let's do this in yellow, dV/dt, and I left the units out of this, and I want to find dr/dt. So plugging in the r for the radius, I'm able to find dr/dt eventually to be 2 feet per minute. Okay, and then that gives us the answer to the first one, just 2 feet per minute. And then the second question is asking the surface area is increasing at a rate of what feet squared per minute at the same instance when the radius is 4 feet. So then you have S is equal to, this formula, S is equal to 4, here, let's try this. S is equal to 4 pi r squared. So then ds dt, taking the derivative with respect to time at both sides of the equation, you get 8 pi r dr dt. And so plugging in for the r and the dr dt, you easily get ds dt is 64 feet squared per minute. Okay, and there you have it. That's the first one. So that's a related rate. Second one is an optimization problem. And for this one, the figure shows a rectangle inscribed as an isosceles right triangle whose hypotenuse is 26 inches long. So let me go over here first. The isosceles right triangle looks like this, where you have 2 sides that are the same, and then this is your hypotenuse, right? So we know when we have an isosceles right triangle that the base angles are going to be congruent, and they're both 45 degrees. When you have that kind of situation, the slope of one of those sides is going to be -1. So that's where I start, because you want to know, express the y-coordinate of p in terms of x. Well, you know, this little distance is x. Let me get a highlighter on here. This is a distance x. You see the x below here? And that means that this distance is x. So the whole base is going to be 2x. The whole base will be 2x long. Okay, but we need a point y-coordinate up here. So since the line is -x plus 13, or you could write 13 minus x if you wanted to, then that means that's what the y value is when the x is just x. So this point is then going to be x, and then it'll be 13 minus x. Okay? All right, so we got that one. Express the area of the rectangle. We're just going to take the 2x then times 13 minus x and multiply them together to get that area expression. Now, since when we're reading this last question, what is the largest area the rectangle can have and what are its dimensions? Then what we need to do is optimize in that second expression. We're going to optimize that area. Now, since area is equal to base times height, we're going to take these two and multiply. Oops, didn't mean to erase that. Take these two, 2x and 13 minus x, and we multiply them together. Okay, let me see. So we're going to go here. Then, so we start off with our area equation right here. That's area in terms of just one variable instead of two variables, x and y. We've got it just 2x times 13 minus x. We multiply it and we get 26 minus 2x squared. Then, so we've got it in one variable. We simplify. Then we're going to take the first derivative and get the critical numbers. So when we do that, because remember, the maximum or minimums occur at the critical numbers. So if I look, we have our critical number is 13 halves, right? So we know that the domain, I'm going to say on 0 to 13, because both endpoints are where you're going to produce an area that's going to be 0, because you can't get bigger than 13. If you do, you'll have a negative height. And of course, when x is 0, you'll have no width at all. I mean, length along the base. All right, so here you could look at the fact that you have a double prime is equal to -4 then. So a double prime being equal to -4, that means that A is concave down everywhere. Therefore, this x is equal to 13 halves produces a maximum area, because if the graph is concave down like this, that relative or that critical number is going to be at a maximum point where a prime is equal to 0. Okay, so with that, then for C, the largest area a rectangle can have, we need to find the base as well as the height. We have the height is going to be, the base is going to be 2 times whatever x is. That's going to be 13. And then the height is going to be 13 minus 13 halves, which is just going to be 13 halves. So then you have those. That answers the question. We have the dimensions are 13 by 13 halves units. Okay, that is number 2. Okay, number 3 is a linearization problem where you're looking at finding the linearization of the curve at a particular point. So let me go back to, let me get some yellow. So we're talking about that neighborhood of a point, right? And that neighborhood of the point is going to be 4f of 4. Okay? That's just the neighborhood. Now, I have another picture down here at the bottom of the page where I've kind of blown it up a little bit and kind of exaggerated the curve as well, just so you can look at it a little bit better. But where we want to start off with this is what we did the other day in class when you had the lesson on 4.5. And I gave you to find a linear, or the tangent line for the curve is really the linearization L of x. You want to find the tangent line in a particular place. So when you look at the linearization of a curve, we often say L of x is equal to. We call it a function. We use L for linear, and L of x is just Ry. So let's go back to what we did the other day, where you have L of x is equal to f of a plus f prime of a times the quantity x minus a. If you look at it, here's what we did last week, where we were using the point 4f of 4. And here, down here, looking at this, I know that it's going to be at the point 4, 6 when I figure out what that point is and plug in 4 into f of x. F of 4 is going to be 6, the square root of 36, or 6. So I've got y minus f of 4 is equal to f prime of 4 times the quantity x minus 4. And so then I have y is equal to, I'm going to take and transpose the f of 4 to the right-hand side. And then I eventually work it down to where I plug in f of 4 is 6, and f prime of 4 is 2/3. Now, I've got that information over here. I've got them checked in pink here and here. Okay, so I did the derivative up top here. Here's f prime of x. Simplified, it's f prime is x over the square root of x squared plus 20. Okay, so I put in the 4 there, and I got 2/3. So that gives me my slope at 4. So this is your linearization here. And you can simplify that if you like. You can write it differently. I think I have that somewhere on here where you can write it differently. You could solve it for y. You can make it y is equal to 2/3 or 2/3 x minus 8/3, and then 16 is 18/3. So 18/3, so 10/3 would be your y-intercept. So 2/3 plus 10/3. But anyway, so, and that's what I think the answer is on the last page. So we have our L of x, and then what we want to do here we'll go back, and let's go back to the first question. We have our L of x, and I put that in the blank right here. You can write it like that, or you can write it in the slope-intercept form. I prefer that method because it's most useful. Let me zoom in on my work here for this part. So if I'm going to find L of 4.2, that's what that's really saying. If you think about x is equal to a, so at a, for the second, wait, hold just a second. I've got L of x. So how accurate is the approximation for L of a plus 0.2 and f of a plus 0.2? So what they're really saying in this is L of 4. And if you look down here, I kind of wrote that in. L of 4 plus 0.2. So I'm approximating, that would be L of 4.2. And we want to know how close is that to f of 4.2. Same thing, 4 plus 0.2. So if you look at down here, I've got the graph, and you can see that the tangent line is underneath the curve. Again, it's exaggerated, but so where you have the point 4.2, L of 4.2, it's on the orange line beneath the f of x graph, 4.2, f of 4.2. So that little star that you see on that difference is this quantity. It's the difference between the function f and the line at 4.2. So I have L of 4.2 that I've calculated to be, and use the equation. You can see that I've got down to here, and that turns out to be 6.13 repeating. And then f of 4.2, I just put 4.2 into the function up here. Into the function, I got 6.13514. Yeah, I'd use a calculator for that. So all that I'm doing is I'm saying, what is the difference between this, f of 4.2 and L of 4.2? And it turns out to be this. So they're just asking you to think in this. It says, how accurate is the approximation? And they're giving you a choice on which one. And this is this value, 0.00181, is less than only 10 to the negative 2 power. So if I write this here, this is less than 0.01. And it's not less than any of the others. You can see I have the decimal digits there. So the answer there would be 10 to the negative 2 power. All right, right here. Okay? All right. So really a loaded question. When you're writing the equation for the tangent line, you got to remember, I would probably focus on this second line a little bit more, that it's easier for students to understand that. But it's also important, you're eventually going to have to get really comfortable with that type of notation, and the linearization of the line is L of x is equal to f of a plus f prime of a times the quantity x minus a. Okay? So I don't want to go too long into this. You've got a few more problems that I need to go over, so I'm going to do 2 videos on this just to make sure that we have enough time to discuss it. The next one is an optimization, then we have 2 related rate problems, and then the last problem is just a differential problem. Pretty easy on that as well. Okay, so I'll pick up with this on number 4 when we get back to part 2.